Hello everyone, this is Professor Tharm Ratnarajah from University of Edinburgh, UK. I am continuing with our tutorial on tools and techniques for future spectrum sharing and coexistence. And in this video part of the tutorial, I'm going to talk about a transceiver design for full duplex cellular and MIMO radar coexistence. So coexistence of cellular system and MIMO radar system. The cellular system is equipped with the full duplex base station. So this is the outline of my talk. I will start by talking about our system model that we studied in in this work, and then I will talk about spectrum sharing MIMO radar system, and then I will move on and talk about spectrum utilizing full duplex MIMO cellular system. Then I will talk about some robust beamformer design at the full duplex MIMO cellular system, and then I will talk about the spectrum sharing algorithm that we studied in this work, and I will show some numerical results. So radar band for spectrum sharing, and in UK and US and Europe, different bands are considered for spectrum. Different radar bands are considered for spectrum sharing. For example, in UK, the S band and the C band are currently occupied by the variety of radar application. For example, civil maritime radar or aeronautical radar, which are operating at 3.4 GHz band, and the weather radar is operating at 5.6 GHz band, and the UK Ofcom, which is the Spectrum Regulatory Authority in UK, has proposed to release some of these bands for commercial use. So the radar spectrums are going to be shared with the cellular system or mobile broadband service provider to support future demand in the cellular system. In US, the FCC has proposed to use the 3.55 GHz to 3.65 GHz band for commercial broadband use. This is the CBRS band. The Commission Spectrum Sharing Initiative is motivated by many factors, including the Presidential National Broadband Plan, which called to free up 50 MHz for federal health spectrum by 2020. The report on effective spectrum utilization by PCAST, which emphasized to share 100,000 MHz of government health spectrum, which are utilized by the federal incumbents, by naval ships, etc. So there are a lot of push of releasing the government spectrum or radar spectrum to cellular system going on around the world. In the Europe, the spectrum policy regulators in Europe has proposed to use 2.3 to 2.4 gigahertz radar band for commercial use as well. Okay, so this is the system model that we have studied in this work. Here is the cellular system, which is a single cell cellular system actually. This one is the base station equipped with M node transmit antennas. Here, these are the transmit antennas, and there are N node receiving antennas serving J downlink users. There are a bunch of downlink users. They are J downlink users. These users are half duplex users. This base station is full duplex, and there are K uplink users, and they equip with MK transmit antenna. These downlink users equipped with NJ receiving antennas. So these users are half duplex. This base stations is full duplex. Here is the MIMO radar, has a RT transmit antenna and RR receiving antenna for detecting a point light target in the far field. So when you talk about spectrum sharing between the radar and cellular system, there are many interference channels appearing. One of the interference, if you use full duplex, this is the self interference. So this is a self interference channel, and this is the co-channel interference between that uplink users to downlink users. This is the co-channel interference. Interference to MIMO radar from the base station. So these are the interference to MIMO radar from the base station. This is the interference channel. Interference from the MIMO radar. So interference, if the radar is operating, it will interfere with the receiving antenna at the base station, and also interfering with the receiving downlink users as well. Interference to MIMO radar from the uplink users. The uplink user, when they transmit it to the base station, they also interfering to their radar system as well. So our objective in this work is to show the coexisting performance the mobile cellular system is able to operate to provide service to uplink and downlink users, and also the target MIMO radar is able to detect the target as well. So we wanted to show this coexistence. By doing, how do we do this? We need to somehow minimize these interferences. So if you can minimize these interferences, then we will be able to show this coexistence of these two systems. So this is the issue in spectrum sharing. If you try to share the spectrum, the interference. So we need to manage this interference effectively. Then the coexistence is possible. If we are using full duplex on top of that to enhance further spectral efficiency. Okay, spectrum sharing MIMO radar system. Let's talk about the radar system first. To map the transmitted waveform onto null space W. So there are interference from the radar to downlink users, from the radar to base station. So these are the channel. So we wanted to send the radar signal, wanted to send the null space of this interference channel to avoid interference towards the cellular system. So this is the, how do we do that? We use the projection matrix, which is the RT is the transmit antenna at the radar. By RT matrix, signal transmitted by the radar system is given by this projection matrix into the transmitted signal. So this projection matrix is enabled to transmit the radar signal waveform in the null space of this interference channel. Okay, interference channel from radar to base station and interference channel from the radar to downlink users. So the target detection binary hypothesis testing is used here. H node is no target but active cellular system. The alternative hypothesis H1 is both target and the cellular system are active. So the radar receives signal YRL is given by in the alternative hypothesis. This is the radar is active, so radar reflected signal here. So this is the interference from the base station because the coexistence is happening. This is the interference from the uplink users, and this is the noise term. Okay, this is the noise term. NR is the noise term. In the null hypothesis, the radar is not active, so only the cellular system is operating. This is the interference from the base station, and this is the interference from the uplink users. This is the received signal. So, spectrum sharing MIMO radar system continuing. So, A pi denote the transmit and receiving steering matrix defined by this. AR pi and AT pi are the steering vectors. We assume the transmit antenna at the radar and the receive antenna at the radars are equal, which is denoted by R, and then the steering vector is given by this A pi. The ith element at the rth column of the A matrix can be written as in this form here. The Zi are the location of the ith element of the antenna array. Lambda is the wavelength here of the carrier frequency. So we will be using generalized likelihood ratio test to determine the probability of detection. So the sufficient statistics of the received signal can then be found using the match filter. This is the radar receive signal after match filter. This is written in this form here. So this is Y radar signal and multiply by this XR. So if you vectorize this guy Y, capital Y hat, you can write it like this. This psi matrix psi is given by this expression here. This is the non-white covariant matrix. This is the colored matrix here. So this matrix, this X psi tilde is given by this. This is the noise plus interference matrix here. This is the psi tilde is given by this expression here. Here are the interference matrices appearing here. So we wanted to whitening this signal, so convert the covariant matrix into white. We apply whitening filter. By how do we do that? We do a Cholesky decomposition of this guy. So the pi is the lower triangular matrix of the Cholesky decomposition of the psi inverse. So psi inverse Cholesky decomposition here. By multiplying that, we can whitening the colored as noise perhaps interference. So if you whitening the received signal, the hypothesis setting problem 1 can be equivalently written as this form here. This is for alternative hypothesis. This is for null hypothesis. The A bar is given by this formula here. If P for this null probability density of the Y hat under null hypothesis and probability density function of Y hat in the alternative hypothesis is denoted by these two expression here. Then alpha R and pi R are given by this maximum likelihood estimation. So the GLRT test the local likelihood function for target detection can be formulated in this formula here. The delta here denote the decision threshold. So this whether the target present or not is depends on this test here. This is the GLRT test. This is the log likelihood function. So the asymptotic statistics for this locally function is given by this expression here. Under the null hypothesis, this is a chi-square distribution, non-central chi-square distribution. Under the null hypothesis is a central chi-square distribution. So this is central chi-square distribution with a 2 degree of freedom, and this chi-square rho is a non-central chi-square distribution. So the rho is the non-central parameters is given by this expression here. So the threshold is based on the false alarm probability. So this is the inverse denote the central chi-square distribution in sorry, this is denote the inverse central size square distribution. PFL is the probability of false alarm. This is a non-central size square distribution. So this is the relationship between the probability of detection and the probability of false alarm, which involves inverse size square distribution and also non-central size square distribution as well. So now I'm going to talk about the projection matrix. So we need to get the projection matrix such that the interference towards the cellular system is minimized. So to mitigate the interference toward the cellular system, we need to design the projection matrix. How do we design the projection matrix? This is the matrix W involve all the interference channel, and first you do the SVD of this one. R and X are the this is the SVD of W. R and X are the unitary matrix, and diagonal matrix omega contain the singular values. And the projection beamformer matrix, the null space projection matrix, beamformer matrix is given by this expression here. X is this SVD singular value decomposition unitary matrix. X is given here, appearing here. Okay, so there is small proposition. So the full detail of this presentation can be found in this transaction paper that we published a couple of years ago. So when the transmit antenna at the radar supposed to have a large antennas compared to a node in the receiving antenna at the base station, and J into J is the downlink users, and NJ is the receiving antenna. So this is the receiving antenna at the base station, this is receiving antenna at the downlink user, and J is the number of downlink user. So the beamformer matrix P is the RT into RT. RT is the transmit antenna at the radar. Is given by can be projected orthogonal onto null space of the entire cellular system involving the full set of interference channel. So this is the way you obtain the P projection matrix. So let's talk about spectrum utilizing full duplex MIMO cellular system now. So the received signal at the base station and the received signal at the downlink users can be written as this form here. So let's talk about using spectrum of MIMO radar system, the signal received at the full duplex base station and the jth downlink user of the cellular system at time index L can be written as this here. This is the base station receive signal. This is the kth uplink users. This is the uplink kth uplink user channel, goes from 1 to capital K. This is the uplink transmitter signal. This is the transmit impairment at the uplink user, and this is the self interference channel. This is the downlink transmitted signal X node, and this is the base station transmit antenna impairments, and this is the receive impairment at the base station. This is the interference from the radar system, and this is the noise. So if we talk about downlink user receive signal, this is the downlink user channel into downlink transmitted signal, and the transmitter impairments at the base station here C node, and here also C node as well, same thing, and the kth uplink user signal interfering the downlink sisters. This is the co-channel interference. This is the uplink user transmitter impairment. This is the receiver impairment at the user, and this is interference from the radar system, and this is the noise. Okay, so the uplink transmitter signal is pre-coded here. This is the information pre-coded, and the radar signal, the base station downlink user also pre-coded here for the jth users. Okay, all jth user downlink signals are denoted by X node L. This is the uplink channel, and this is the downlink channel here. Okay, so there are N node base station receive antenna, MK transmit antenna, and there are M node transmit antenna at the base station, NJ receiving antenna at the downlink users. So here are some more symbols that I already mentioned here. This is the interference from the radar transmitter signal to the receive antennas. This is the radar interference to downlink users, and this is the precoder matrix for the downlink user, and this is the information of the downlink user for the jth downlink user, and these satisfy these second order statistics. This is the uplink precoder. This is the uplink information to the kth user, uplink user, and this is also satisfy this second order statistics as well. This is the noise, zero mean and covariant matrix are given by here at the base station and the downlink jth downlink user. This is that distortion at the transmitter at the kth uplink user. This is C node is the distortion at the base station at the transmitter as well. These are the receiver distortion at the jth downlink user and the base station receive antennas. So the spectral efficiency, the achievable rate for the kth uplink user at the base station and the jth downlink user is given by this expression. This sigma, capital sigma uplink and capital sigma downlink is the interference plus noise covariant matrix. The for the uplink case is given in this expression here. This is the interference plus noise covariant matrix. Similarly, you can derive the downlink interference plus noise covariant matrix, which is given in the paper, but I'm not showing in this slide here. So joint beamformer design. So we wanted to design a beamformer such that we wanted to maximize the probability of detection at the radar. For the uplink user, rate will be guaranteed above this predefined number. The downlink rate also guaranteed by this predefined number here. The precoder transmit power constraint is for the uplink user is given by this expression. There are K user here, and there is a downlink transmit power constraint at the base station is given by this. So these are the power constraint, these are the rate constraint for uplink and downlink, and we wanted to maximize the probability of detection. So we are doing maximizing all these things with respect to the precoders. So we wanted to design a joint precoders at the uplink users and the base station such that this optimization problem is satisfied. So PD is probability of density, probability of detection is a monotonically increasing function with respect to non-central parameters. So the problem can be reformulated as this here, maximizing V subject to this. This is the non-central parameters here, subject to this old constraint here. So there's a lemma here that we derive. This non-central parameter is lower bounded by this expression here. This IR/DR is a total interference power from the cellular system to the MIMO radar system. This radar is given by this expression here. The proof is again given in this paper. If you are interested, please have a look. So now that problem of maximizing the probability of detection of the radar is turn out to be minimizing this interference term subject to all the constraints that I mentioned before. For analytical simplicity, we wanted to rewrite this constraint in mean square error term. So to calculate the mean square error, we first apply a linear receiving filter for the uplink and the downlink to obtain to this receive signal to obtain the source symbol, the optimum receiver beamformer matrix at the base station for the kth uplink user, and the jth downlink user is given by this expression here. So these are the interference plus noise covariant matrix that I mentioned before. V is the precoder matrix, H is the channel matrix. So the problem of maximizing the probability of detection is turned out to be this form now, minimizing this capital gamma. Gamma is lower upper bound by this I radar is upper bound by this gamma. So the rate constraint is now, we write it as the mean square constraint here. These are the rate constraint, these are the power constraint here. Okay, yeah. So again, we are considering, so far we consider perfect channel. Of course, there's a channel estimation error will be appear in all the situation channel knowledge. So we wanted to design a robust design. So we are considering a non-bound channel estimation error here. So these channel are the channels are going to be with the errors, and the errors are bounded by this delta and the rho here. So we are now using the introducing the channel estimation error as well, and by using this lemma 2, this F is a D into D positive semi-invariant matrix. F is less than, the magnitude is less than 1. Then this F, then the maximization of function F is equivalent to this here. By using this lemma, we can rewrite this problem again as a robust problem, because we are introduced a channel estimation error as well, a non-bounded channel estimation error. So this is the robust problem that we formulated by using this lemma now. By this problem further can be changed to SDB problem by converting this and into a vector form. This defined here. We can change all these to SDB problem. These are the constraint can be written as this way, and by using the linear matrix inequalities, then we can write by using this again some more linear matrix inequality lemmas, and we change all these problem into a semi-definite program. So minimizing tau subject to these constraint. So all these constraint can be written in this way here. Okay, so here are the power constraint. All these rate constraint can be changed in this form here. So this is SDB problem can be solved in polynomial time here. So I'm going to show explain the spectrum sharing algorithm now. So algorithm 1 perform the null space projection toward the interference channel of the cellular system, thereby cancelling interference from the radar to the cellular system. This is the algorithm here. This is the algorithm to find the projection matrix. Algorithm 2 produce the optimum beamformer matrix at the transmitters and the receiver of the cellular system to minimize the interference from the cellular system, the base station. So this is the algorithm 1 here, and this is the algorithm 2, how to obtain that U precoder matrix and the combiner matrix. So we propose these two algorithms. Now I'm going to show some simulation results. So the simulation setup, a single hexagonal cell of radius R is equal to 40 meters. Full duplex base station is located at the center of the cell, and MIMO radar system is located 400 meters away from the circumstances of the cell. This is the path loss model that we consider here. We consider D naught is equal to 1 meter, bandwidth is equal to 100 megahertz, the carrier frequency is 3.6. This is the CBRS band. You may recall the parameter alpha C for line of sight, non-line of sight for the path loss is given by 2.0 and 3.1 respectively. Shadowing fading standard deviation is 2.9 dB and 8.1 for line of sight and non-line of sight. For the cellular system, thermal noise density is minus 174 dBm per hertz, etc. So we are considering transmitter receiver hardware impairment as well, and the channel estimation uncertainty bounds are given by 0.1 here. Yeah, so the radar antennas is 8 and probability of false alarm is 10 to the power minus 5. The velocity of the target is 782 knots and the distance of the target from the radar system is 900 meters. So this is the conversion of the proposed algorithm. So you can see the proposed algorithm, the algorithm 2 of the designing the beamformer and the precoder is the iterative algorithm. So it is converging quickly within 16, around 8 or 10 iteration. It converged to the required precoders and the beamformer matrix. This diagram shows the complexity. So this is the number of complex multiplication for number of users in the cellular system, and here is the number of complexity multiplication. Okay, so this is the red triangle show the cellular users, and this is the black square shows the full duplex base station, and the blue stars are shows the complexity of the radar system. And the top is showing the number of antennas as well. This is the kind of a number of antennas at the base radar system. This is the multi-dimensional diagram here. Okay, so here is the probability of detection versus radar transmit power. So this blue diamond is with the spectrum sharing with the number of antennas is 8 at the radar. This is with the spectrum sharing number of antenna 4 here. So you can see number of antenna reduced. You need to transmit more power here. So this is without the spectrum sharing number of antenna 8 here, this one, and this is the 4 here. This is the 4 here. So you can see by doing spectrum sharing, we need to transmit more power. So this is the case for 8 antenna, red curve 8 antenna. This is the curve for 4 antenna, and this is the curve for 8 antenna for the spectrum sharing. So you need to transmit more power to get the required probability of detection. So that is the penalty that we are paying here. To do a coexistent cellular system, users enjoy the service by sharing the spectrum with the radar. The payment is the radar have to increase the transmit power. So here is again probability of detection was the probability of false alarm. So probability of false alarm is, so here are the two curve here. Probability of detection with the spectrum sharing is the red one. Probability of detection without the spectrum sharing is the green one, for different transmit power. This is the 5 dB. This is the 15 dB radar transmit power. So probability of false alarm, we are talking about very low probability of false alarm. So like a 0.1, even less than 0.1 here. So we are the interested area is this area in terms of probability of error. In terms of probability of detection, we are interested in this area. So you can see we need to transmit high power to get the required probability of detection. Okay, so this is the average throughput for transmit receiver distortion. We consider distortion at the transmitter antennas and the receiving antennas. There are these blue horizontal lines are for the half duplex system. This is the 2 antenna system. This is the 4 antenna system. This is the full duplex system, and this is the for the 4 antenna case. This is the full duplex system for the 2 antenna system case. So when you have the hardware impairments are very low, you can see a doubling effect of spectral efficiency compared to half duplex. When the hardware impairments are high, you can see the full duplex benefit is disappearing. The half duplex system is better off. When we have a larger hardware impairments, mean you end up with a larger residual self interference which are difficult to cancel. Then in this case, half duplex system is better compared to full duplex system. This is the throughput versus CSI attenuation. So I told you the uplink user will interfere with the downlink users. So if you have a less interference, you can do this by assigning the uplink downlink users far away by using some clever scheduling techniques. So by doing less self co-channel interference, full duplex is benefit you can see high, and when the attenuation co-channel interference is present, the performance is degrading here as well. So this is the half duplex. These are the full duplex with the different hardware impairments. So this is the small hardware impairment, and this curve is for high hardware impairment compared to this one. So let's talk about the conclusion now. So null space-based waveform at the MIMO radar system and robust transceivers for the full duplex mobile multi-user MIMO cellular system were designed to facilitate a two-tier spectrum sharing framework. Numerical results demonstrate the effectiveness of the proposed algorithm, spectrum sharing algorithm, to tackle the imperfect nature of the wireless channel and hardware at the cellular system. A certain trade-off of the radar transmit power and probability of detection and quality of service of the cellular users are analyzed in this work as well. So to get the quality of service required data rate for the cellular users, we need to cancel the interference, manage the interference, and probability of to enhance the probability of detection, radar have to transmit more power. Using the spectrum spectrum shared by the radar system, full duplex cellular system was able to achieve an area throughput of around 4 to 5 megabits per second per meter square for reasonable SI cancellation of around minus 70 dB. However, to facilitate this while also maintaining a detection probability of 0.90 above, the radar have to transmit more power. So in a nutshell, design framework provide a cornerstone and importantly essential understanding of successful development of future cellular system in conjunction with MIMO radar system that can operate under same spectrum resources. So that's all I would like to say in this talk. I hope you have enjoyed this presentation of spectrum sharing between cellular system and the radar system. This is the case in the CBRS system in the US, and this is the case in the LSA in Europe as well. So we end up using the radar spectrum, so you can orthogonally use whenever the radar is not using the spectrum. You can use the cellular system can operate, or you can share the spectrum, operate simultaneously by managing the interference. So that is the work that we have presented in this tools in this tutorial. So this tutorial is about tools and techniques for speech future spectrum sharing and coexistence, and we have presented one of the coexistence of radar and cellular system in this presentation. Okay, thank you very much for listening. I will see you next time in